First, I want to start the talk by saying, thank you for all the organizers for the invitation. I've been born quite a few times. I'm always impressed by how well things are organized in Germany. So, okay. So the talk is about the modular space of positive scalar curvatures. So actually, recently, there has been, in the past few years, there has been a lot of activities going on about positive scalar curvature metrics on manifolds. So let me just recall some very basic things. So throughout the talk, the manifold M will be a closed spin manifold. Of dimension at least 5. The reason for this is because of surgery theory. Now, let's say this is the space of all Riemannian metrics on M, then we know that this space is, as a topological space, is contractible. So topologically speaking, this is not very interesting. Now, this is the space of positive scalar curvature matrix. Now, of course, there's a question whether, given a manifold, closed spin manifold, does it ever support a metric of positive scalar curvature? That's the existence theorem, and we know that certain spin manifolds, you cannot have positive scalar curvatures. Throughout the talk, since we're interested about the space of positive scalar curvatures on a spin manifold, so let's say we have this manifold, at least this set is. So throughout the talk, this space is not empty. Now, of course, there are some wonderful theorems about when this manifold supports a positive scalar curvature, but I'm not going to talk about that today. And as I said, there's actually a quite extensive literature on the properties of this space. For example, the first thing we want to study is it connected or not, or what about the higher homotopy groups of this space as a topological space. So what we want to know is the pi I of this space. And so without going to this big list of results, so let me just quote some of the most relevant, some of the results that are most relevant to my talk today. So here's the theorem. Oh, actually, before that, sorry. So we have this space of metrics, or positive scalar curvature metrics on M, and we know that this is the group of diffeomorphisms of this manifold. Of course, it acts on the space of positive scalar curvature metrics by just pull back the metric. So if you start with a metric of positive scalar curvature, you pull it back, you get another one, which is also positive scalar curvature metric. So let me just denote so if you study the quotient space, look at this quotient space, this is called the modular space. A positive scalar curvature matrix on M. So in this talk, actually, we'll be studying this space instead of, so you can, of course, ask the same question. the higher homotopy groups, or pi. So in it, really, for this talk, I will be focusing on pi 0, which means whether this space is connected or not. And so the techniques, of course, we should be able to generalize these techniques to study higher homotopy groups, but there's, of course, difficulties that's related to somehow all these conjectures, you know, the Farrow-Jones conjecture, and how the fundamental, the higher homotopy groups of diffeomorphism group of some other manifold. So these properties these are all related, but I'm not going to get into that. So let me focus on pi 0.
What is the topology of positive matrix and this disproportion?
Oh, you mean the topology? Oh, so it's just a subspace of the space of Riemannian matrix. On the Riemannian matrix, a metric is you can really think of as a map from the manifold to positive definite symmetric matrices. So then you just give, so you just give this compact open topology.
And the quotient is okay? The quotient space, the quotient space is Hausdorff and
the quotient space is Hausdorff. Okay, I cannot be for. I'm not so sure, but okay. Let's not worry about that for now.
R plus m is open in Rm.
What's that?
R plus m is open in Rm.
R plus can be.
R plus is open in all metrics, so if you perturb positive scalar curvature, metric remains positive scalar curvature.
Perturb a tiny bit, yes, I think so, yes. Mm-hmm.
So you have some kind of Frichet manifold, and well, diffeom is a kind of Frichet Lie group acting on that.
Frichet Lie group.
This is how you can have so much, but it's not completely right.
Okay.
You need to take the converse to the identity.
You.
Diffeomorphisms. I don't think.
Yeah, otherwise if you look at the collective double with the identity in the diffeomorphisms, that one's too large.
I can study any diffeomorphism. That would be okay. But that's not okay. Well, that's not a problem. Why would I have to restrict to the identity component?
No, things will not be very. And otherwise you get something highly known Hausdorff.
Okay. Whether it's Hausdorff or not, okay. So really what we're interested in is so the point is, okay, so you're saying let's restrict to the identity component of the diffeomorphism group. So okay, so really what I'm interested in, or a lot of people are interested in, is to distinguish positive scalar curvature metrics. So give you a space like this. How can we find many very different? Start with one, and then how can you find different positive scalar curvature metrics? By different, we mean okay. In this sense, for example, they are in different components, which means you cannot connect by a path of positive scalar curvature metrics, then which means they are very different. Now, in this sense, it means okay. Not only you cannot, if they're in different components of this guy, not only they cannot be connected by a path of positive scalar curvature metrics, even after you pull back by diffeomorphism, these things cannot be connected either. So really, things here are even more different than things over here. That's really what we're interested in. So whether you want to quotient out by the identity component or quotient out by this whole group, this is not the main concern. Yeah. Okay. So yes. All right. So let me just move on. Let me just quote a theorem. This is so with the same M, closed spin manifold, dimension at least 5. then so this theorem says if the fundamental group has a torsion element in it, then this space has infinite many components. So which means you have many different positive scalar curvature metrics. They are different even after you modulo the diffeomorphism group. Okay? So, and the main result of my talk here is to generalize this by using higher index theory to gain more information about the modular space or the space over here. So, but before that, actually, let me introduce a group. Actually, this was defined by Weinberger and Yu. So there is a group. And you take the, so let me just say there's a, is it eraser? So modulo some equivalence relation, you can get a group. There's an abelian group that you can get out of all the positive scalar curvature metrics. And the equivalence class here is by concordance. By two positive scalar curvature metrics are concordant if you put the two positive scalar curvature metric on a cylinder. And then if there is a positive scalar curvature metric on the cylinder that restricts to this two positive scalar curvature metrics on the boundary. So then they are called concordant. And then there's the addition here is a bit more involved, so let me not get into that. So there is a abelian group. So it's really, we can think of this as, in a very bad analogy, it's like the K-theory, the construction of K-theory. Okay. So again, the diffeomorphism group acts on this group. Okay, now the point, it turns out this action is not a linear action, so it doesn't preserve the origin. You can imagine, I mean, how do you get the origin? You really have to specify a base point. That's how you get the origin. So it's going to move this base point. But it's an affine action. So there's an affine action on this abelian group. Now, what we're going to do is we define the, so this is called the moduli, sorry, this is the group of positive scalar curvature metrics, and we're going to define the moduli group, which is the quotient of this group. You just modulo out all the classes okay. Take all differences like this, they generate a subgroup, and just quotient out by this subgroup. This is the moduli group. So now, what we're interested in is this is an abelian group. We are interested in the free rank of this abelian group. So that, in some sense, is a more refined information about the size of the connected components. So for example, if the free rank of this abelian group, or this abelian group, is, if the rank is at least 1, then of course you will get this for free. Hopefully that's clear. So we are interested in the free rank of this group. Okay? So here's the theorem by Weinberger and Yu about the free rank of this group. So they prove that the rank of this abelian group is at least the rank, so to be precise, is 4K minus 3. So to reduce the question, well, at least they give a lower estimate of the rank of this group in terms of the K-theory of the, so gamma here is the fundamental group of M. So they reduce the question of studying the rank of this guy as the rank of some, so this is the finite part, the so-called finite part of the group sister algebra of gamma. So I'll define what this is, of course. But before that, so let me, here is, this is the maximal maximal sister group sister algebra. Say what? Sorry, which one? The rank of this?
No, but it's PM or PT there?
PM. Yes. Okay, I will. My joint, okay, oh, I forgot to say, of course, this is basically joint work with Guoliang Yu. And yes, our result will be about PM tilde. Okay? Is this the right order? I think I'm doing it right. Okay. So now, before actually I define what this finite part of this K-theory is, let me just, so here's the theorem. So the question is, what is this finite rank? And the rank of this finite part. So let me just state this. The theorem Guoliang, Weinberger and Yu. So if gamma, again, throughout, gamma is the fundamental group of, let me just say this, pi 1 is not torsion free, then is at least 1. Well, as I said, if the rank is at least 1, then you have a copy of Z sits inside over here. So it's, you know, it's agrees with what we have over there. Okay. For P, now this is for the space of positive scalar curvature metrics instead of the modular space. So a similar result, right? Okay. So now, if we want, of course, we want to get a more refined information out of this finite part of the K-theory. So now, torsion elements, this is essential here because of conjecture like bound-cone conjecture, Novikov conjecture. So if it's torsion-free, then you would expect this thing is actually 0. The finite part would be 0. Okay, but anyway, I haven't defined you what the finite part of the K-theory is, but I'll do that very soon. So let me finish this. If it's finitely embeddable into, again, I will define what this is in a moment. So this is a condition, this is a geometric condition on the group. Then the rank of this finite part is some number. Okay, what this number is, where this number for a group is precisely the number of integers that can be realized as the order of some torsion element. So it's, intuitively speaking, this is counting how many different, up to conjugacy, how many different torsion elements that you have. So it's really counting the number of order of elements that can be realized as torsion elements in your group. Okay? So for example, if you have lots of torsion elements and they give you different orders, then this group is big. Okay, so now combining these two theorems, we get that, for example, if the fundamental group is not torsion-free, then the rank of PM is at least 1. If you have a stronger condition, finally embeddable into Hilbert space, then the rank is this big, at least, of PM. So now, of course, now I have to define you what this finite embeddability is and what this finite part of the K-theory of this maximal group system algebra of gamma is. But actually, let me postpone that for 1 second. Let me state the theorem for PM, PM tilde. So if again, I'll explain what this notion of strongly finitely embeddable into Hilbert space is. Here, I forgot to say that I should, that's part of the theorem. So the dimension of the manifold is odd. Towards the end, if I have time, I will comment on what happens when the dimension is even. There is some, not as general as this result, but there are some partial results. Put an actual condition on the fundamental group, then we can get results for even dimensional manifolds as well. Again, all these manifolds being dimension at least 5. Okay, so with this, then the rank so if it's not torsion-free, if we really just want to say then we have at least one So at least this part recovers the original theorem of Piazza and Schick. So this is the main theorem. Okay, so now let me define what the finite part of the K-theory is. So start with the group. This is the maximal group system algebra. The finite part of the K-theory is defined to be the subgroup of the K-theory generated by the projections that come from torsion elements. If you have a torsion element, by all elements like this. So if you have a torsion element, you can, this is a standard construction, you get a projection in the K-theory. You take all these elements, and you take the subgroup generated by these elements. This is the finite part of the K-theory. Okay, for technical reasons, we assume this torsion element is not trivial. So this is the finite part of the K-theory. Okay, so now let me define the notion of finitely embeddable into Hilbert space. So gamma is so if you're familiar with the notion of coarse embeddable groups, so this is a more flexible notion of a generalization of the notion of coarse embeddability, and which is designed to take care of torsion elements. So here's the definition. For any finite set in the group, there exist coarsely embeddable group, let's call it G, and a map phi from F to G such that the following conditions are satisfied. First one, as you can imagine, when you restrict to this finite set F, this map should be a homomorphism. If the product, again, lies inside F, then it's a homomorphism. The second condition is designed to take care of the torsion elements. So if you have, for any torsion element inside F, the order of the image is the same as the order of the original element. So the order is preserved. So basically, on torsion elements, it behaves like it's injective.
So if your group is torsion-free, you could just take the trivial map phi.
Exactly. So exactly, the notion, it's only designed for torsion elements. So if it's torsion-free, yeah, every torsion, okay, this is, if you care about torsion-free groups, yeah, this is all torsion-free groups are finite and embeddable, yes. But it's really designed for this type of theorem, so it's designed for torsion elements. And for all these applications, we need torsion elements in the group. Okay. So let me just give you a list of groups that are finitely embeddable. This is a huge class of groups. Actually, let me write it over here. I need more space. Well, by definition, actually, every coarse embeddable group is finitely embeddable. So if you're not familiar with the notion of coarse embeddable group, it roughly means you can put your group, there's a map, that map your group into the Hilbert space, put the word metric on your group. Now, in a small scale, you can crash things to a point, whatever. But on a large scale, if 2 points are very far away, they remain far away. So that's the coarse embeddability. So let me just be more concrete. Two huge subclasses of coarse embeddable groups are amenable groups and hyperbolic groups. So all these groups. These groups are finitely embeddable. All residually finite groups. You can add, virtually residually finite. Okay, let me not worry about that. So, for example, actually, Gromov. Gromov monster groups actually are coarsely. Okay. This is a class of groups that are not coarsely embeddable, but they are actually finitely embeddable because this notion, in some sense, it's what's the word? So it will remain closed under certain limits. And you know that the Gromov monster groups are certain limits of hyperbolic groups. So because of that, these groups actually are finitely embeddable. And the list goes on, so let me just stop here. I think this is, even just these two classes, it's a huge class of groups. Now, as you notice, of course, the techniques that actually come in to prove these theorems is techniques that come out of Novikov conjecture and Bancon conjecture. But you know that for these two groups, actually, we know, the Novikov conjecture or the Bancon conjecture, actually, even with coefficients, they are true. But we essentially know nothing about, if you're really talking about the Novikov conjecture, say, we don't really know anything about residually finite groups. So again, this is a very flexible notion. So it's designed so that when we do these type of applications, we use the techniques from Novikov conjecture, but we go further. Okay. And one of the things, of course, essential point is we use the maximal system algebra, group system algebra, instead of reduced one. The point is, essentially, how do you distinguish elements in the finite part of the K-theory is by taking traces. For each torsion elements, you can get a bunch of traces, and they will, so at the algebraic level, they will definitely distinguish these elements. But how do you pass from the algebraic group algebra to this system algebra? For the reduced one, there's an issue of extension. But for maximum one, there's still work to do, but for the maximum one, you can do that. That's the reason. Okay, so this is finally embeddable. Now, what is this notion of strongly finitely embeddable into Hilbert space? So let me define it over here. So I think once I define the notion, it should become relatively clear that why we need this slightly stronger condition to prove the theorem for P tilde. So here's the definition. Gamma is strongly finitely embeddable into Hilbert space if for any gamma, this is the free group of n generators. For any choice of n and any choice of automorphisms of your group, of course, once you choose these, there's a standard direct sum product you can construct of the free group on the with the group gamma. So now everything like this is finitely embeddable. So for all choices. Now, the reason we need the semi-product is, you see, we are quotienting out by the diffeomorphism group. So intuitively speaking, if you're quotient out these guys, so in the proof, you will see that at some point you will need to deal with, imagine, so you will try to prove linear independence of certain elements. So what's involved will be a finitely many diffeomorphism group for that linear combination you are considering. So that's why you are, that's why we are considering the semi-direct product. So that's the reason, intuitively speaking. Now, okay, so what groups are strongly finitely embeddable? So all amenable groups and all coarsely embeddable groups are okay. So if you have a group that's coarsely embeddable, then you do the semi-direct product with Fn, it remains coarsely embeddable actually. So again, it's okay. In particular, these groups are okay. Resolutely finite groups, these are okay, and then the proof is it's a simple argument. You just take quotients and so on and so forth, and you can prove it. All resolutely finite groups are are strongly finitely embeddable. These groups, we don't know. Okay. For me, because I don't know anything about the automorphism group of the Gromov monster groups, so. But yeah, I mean, one possible way is try to look at this limit, the construction of how do you construct these Gromov-Munster groups, and you take the hyperbolic groups. Okay, I don't have the courage to do that. Okay. So there's one thing actually. No one asked this question. I was expecting it. So I defined the finitely embeddable groups and strongly finitely embeddable groups. Now the question is, okay, well, are there counterexamples? Are there actually groups that are not finitely embeddable? Yes, indeed. So by Gromov's philosophy, this class of groups are interesting, I think. So, counterexample, this is a group that's not finitely the way you construct it actually is by using the Gromov-Munster group. Okay, the Gromov-Munster group itself is finitely embeddable, but there is some abstract, ugly, huge group that's not finitely embeddable. So first you take G, Gromov-Munster group, take a Gromov-Munster group, and just to make sure we have torsion elements, take the product with, so that we have some torsion elements to worry about. Now there is a way to embed this group into some simple group. Now this simple group might not be finitely presented. So, but we are talking about fundamental groups. So, but there is another way by essentially all these constructions by HNN extensions. There is a big group. You make it even bigger, but becomes finitely presented. Now, I claim that this is not finitely embeddable because if it was, see, on torsion elements, it has to be injective. Now, if this is a simple group, if it's injective, if it's something non-trivial, so it has to inject. The whole group has to inject. But G, so which means this part, at least this part of the group, has to, or if you take, okay, this, if you take enough generators and relations, so on and so forth. So this group has to inject into a coarsely embeddable group. And that's not possible because Gromov-Munster group is not coarsely embeddable. So this is a counterexample. And this is communicated to us by quite a few mathematicians. So after the paper, okay, for group theorists, I think this is very trivial, but okay. So there is a counterexample like this. So how much time do I have?
You will actually 10 minutes.
10 minutes. Okay. So let me, since I have 10 minutes, let me briefly comment on how you would prove something like this. So, okay. So one thing, as you would expect, is related to the bound-cone conjecture. So now, the version we are going to use here is actually, so we're going to use the maximum version, and we know that. So the maximum version, if the group has torsion, we know that it's the assembly map fails. So, and to be more precise, if you take what's used here is the following. Now, we all know that if the group has torsion, you cannot take the classifying space. You should take the classifying space for the proper action, or universal space for the proper action. But nevertheless, let's just take this map, this assembly map. It's not the actual bound Cohen assembly map, but we know that in this case, so this fails to be surjective, in particular when this is not torsion free. So how much it fails the surjectivity is, in some sense, intuitively, is accounted by this finite part. So, and you can see that the point is we want to construct. So the idea of you starting with one positive scalar curvature metric and to construct a new one is the following. So suppose this is my manifold M. Just take the cylinder. This is M cross I. So here's M, here's M. Put a metric here, G0. This is a positive scalar curvature metric. Now, the idea is, of course, on this guy, you can just push it by constant. You can push it to the other end. But, of course, on the other end, you get the same metric. Now, the idea is to get new metrics that are different from this one. You take a non-trivial manifold, of course, matching the dimension of this guy. You glue it in, take the connecting sum, and do some surgery. By surgery, I mean, so just kill elements. Okay, I don't want to get into details, so just so that we keep the fundamental group and so on and so forth, since we're doing higher index theory here. So now what you do is, this is the so-called Gromov-Lawson surgery theory for positive scalar curvature metrics. So there is a way. You start with the one, you can push it all the way to the other end, and everything remains positive. And near the boundary over here, you get a positive scalar curvature metric on M. So you will get a new one. Now, how different is this one from this one is exactly index theoretically. From the viewpoint of index theory, it's exactly given by the non-triviality of this added manifold. So if the index or higher index of this manifold is non-trivial, then the difference of the so-called higher row invariant will be given by this guy. So this is how you create new metrics. And another way, I mentioned higher row invariant. So exactly, so the surjective, so it fails to be surjective. So things that are here, which are coming from the finite part of the K theory, these guys cannot be from over here. So this gives us a possibility to actually, in some sense, pass to the $5 minutes? Yes?
Yeah.
Okay. So to define the so-called higher row invariant is a bit complicated. It's a bit involved. But of course, if you're familiar with this cost geometry, row algebra, localization algebra, so on and so forth. Okay, I don't think I have time to get into that. But anyway, so in this, the surjectivity, it fails. Actually, you can get a long exact sequence. So the surjectivity, the failure of the surjectivity is accounted by some structure group, what Hickson and Rowe call it an analytic structure group. So in some sense, you should, if you're familiar with surgery theory in topology, you should think of this as the analytic counterpart of the structure group in surgery theory. So the higher row invariant lives, there's some higher row invariant. Again, every time I give a talk like this, I have to specify there are two rows involved. One is Zhizhang row. This is the row algebra. This is the Greek row, and this is higher row invariant is the extension of the classical row invariant of Atiyah Patoti Singer. Okay. But okay, Zhizhang row also worked on higher row. So now, one of the this is actually the subtle point of the proof. To prove some theorem, to prove the theorem for PM, you won't actually need the higher row invariant. So here it's, in some sense, what I talked about here is the so-called relative higher index theory. Now, to prove something like this, actually you would need, it's essential to use higher row invariant, because there's, at some point you have to distinguish things over here. You have, basically we map it to something over here. So what we do is, if we want to prove something is linearly independent of here, but if they remain linearly independent over here, then of course they were linearly independent over here, provided that this map is a homomorphism. And the higher row invariant is needed to verify that everything you constructed is a homomorphism. A homomorphism of abelian groups. So here we have to use the higher row invariant. But unfortunately, I don't have time to give you the full detail. Of course, you are more than welcome to discuss with me after the lecture. I think I'll stop here. Thanks.
We're time for many questions. Or remarks.
So for the obstruction for the scalar curvature matrix, there's a twisted version which does not require your manifold to be spin, but the universal cover to be spin. Is there a twisted version of the higher row invariant as well? Spin condition?
By twisted, you mean you take a twisted K cycle? Is that? Yes, I would think so, but okay, I have to, and I haven't thought about this, but I would think so. Maybe there's some technicalities I don't see, but I think should be. No, okay. Okay, let me actually think about it. But that's a natural question to ask. Yes.
Any other question or remark?
Yeah.
Okay.
So maybe you could explain it idealistically. Is there actually a mask from invariant to the finite part that gives you the
Is a map from this to this? No. Essentially, the point is we're going to use elements over here to construct non-trivial elements in this guy. That's the philosophy here. So you see, no matter how, so basically how many different elements over here, you can use them to construct elements over here. So if they are linear independent over here, they will be linear independent over here. But it's all, you read to see, it's not like there's a map from this to this. But it's all hidden in this long exact sequence. So the elements, you see, roughly speaking, there's a map from this p tilde to something like this. Now, you use elements over here to construct these elements. So if they are not in the image of this guy, so they remain in the quotient. And these elements, so they remain linearly independent. That's the intuitive explanation. So basically, the finite part of the K-theory survives over here. That's why.
Any other comment?
Let's thank our speaker.